Okay, so today we'll introduce chapter 21, which is on 3D kinetics of a rigid body. So as you can see, we are following the same outline as before. We studied kinematics and now we move to kinetics in 3D. Okay, so we have a lot of common parameters with previous material, but now we'll develop it more to tackle 3D kinetics of a rigid body. So in this chapter, we will first introduce the methods for finding the moments of inertia and products of inertia of a body about a variable axis. Then we'll show how to apply the principles of work and energy and linear and angular momentum to a rigid body having three-dimensional motion. And then we'll develop and apply this equation of motion in 3D. So to start with, concerning moment of inertia, you already know that for each geometry, for typical geometries, we have expressions for moment of inertia. And in case it's a new geometry, we can do integration. Now, you are not responsible of the integral procedure. So in general, we give you the inertia about axis passing by G, which is the center of mass, and you are responsible to apply the parallel axis theorem to deduce inertia about any other axis.
Okay.
Now, in 2D motion, we just learned about, if you want, inertia about Z, because we just considered 2D motion case. But now we should introduce the tensor of inertia, because we have motion in 3D. So we'll talk about Ixx, Iyy, Izz, and these are, if you want, integral. For Ixx, you perform integral y square plus z square dm. If you want to evaluate Iyy, you do integral ry square dm. So then you consider x square plus z square. And if you want to calculate Izz, should perform integral x square plus y square dm. In general, we provide you, as I told you, don't have to do the integration. We provide you with, for a certain geometry, we give you what is Ixx, Iyy, Izz, and also the product of inertia about axis passing by the center of mass. Okay? But in case you want...
دكتور سؤال
Yes?
دكتور بس بتأكد ان احنا chapter 20 ما خلصناه last time وما I don't think موجودين recording هول
Bala, we are done with it, and I posted the recording in the YouTube playlist. That chapter 20 posted in the YouTube playlist.
اوكي حتى 20.4 انه بقي فكرة نحن عنا اخر شيء.
طب okay, I will check. In case it was not covered, we'll do it again.
اوكي
Okay, but I remember we
اوكي
did it. كأنه, and this is what I remember. Anyway, if not covered, we'll go over it again, okay? Also, we'll do review problems together so we can tackle it again. Okay? So, concerning then the inertia, so as we said, we can calculate inertias about x, y, z, and we are familiar with this one, and in general in 2D. In 2D, we are familiar with this one, Izz. So Izz is equal to integral x square plus y square dm. Now, what about the product of inertia? So when we talk about the product of inertia, it's Ixy or Iyz or Ixz. And it's equal to the elementary product of inertia is x times y dm. So if I want to tell you what is Ixy, you do integration over the mass of xy dm. And because x times y equals to y times x, so Ixy is equal to Iyx. The same for Iyz is equal to Izzy, and Ixz is equal to Izx. Okay? So if you want to evaluate the tensor of inertia for a body, we need to evaluate Ixx, Iyy, and Izz, plus the three products of inertia. So in total, you will have to evaluate 6 terms, xx, yy, zz. In addition, you need to evaluate 3 products of inertia. Because of symmetry, you just have to evaluate Ixy, Iyz, Ixz, and you can then deduce iyx, izy, and izx. Okay. Now, what about the moments and products of inertia? So whenever we consider a body, okay, we have some rules that can simplify the calculation. And if you have a certain symmetry, so for example, if you look at this figure, you have the YZ plane is a plane of symmetry, okay? So for each element, if you want, let's say from this side, you will have an opposite element from the other side, having same Y, okay, but opposite X. And that's why you can say that when you calculate Ixy, it will be equal to 0, okay? Same here for Ixz. So because of whenever we took, same for Iyz. So whenever you have, if the YZ plane is is a plane of symmetry, you can deduce that Ixy and Ixz will be 0. Because for each element, you will have another one on the opposite side for which coordinates will be cancelled, okay? And therefore, you can take this rule to simplify the calculation of products of inertia. Now, in case you have two planes of symmetry, so in case xz and yz are planes of symmetry, then you can deduce that the three products of inertia will be equal to 0. So if you can find just one plane of symmetry, you can deduce that. So here, for example, you have yz as plane of symmetry. So whenever you consider x with any of the axes, if you consider ixy or ixz, each element in positive x will have another one that is symmetrical in negative x. So that's why these two products will be 0. So if yz is plane of symmetry, so if I take ixy or if I take ixz, it will be equal to 0. And if I have, for example, xy as symmetry, if I have the xy plane as symmetry, then I can say that ixz and iyz will be equal to 0. Okay, and if I find two planes of symmetry, then I can deduce that the three products of inertia will be 0. That's why in general we try to put the axis in a way to simplify the tensor. So if we can select axis in a way to have 0 product inertia product, it will be much easier for us to solve. That's why it's important to appropriately select the XYZ coordinates.
دكتور،
Yes.
انت قلت لنا ان المومنت اوف انيرشيا هو الكاباسيتي تبع اوبجكت تو اوبوز روتيشن. هلا البرودكت اوف انيرشيا شو الفيزيكال مينينج تبعه؟
Yes, so here, since you have rotation about in 3D, so since omega can have components in x, y, z, still inertia has the same explanation. But now, because the rotation can have any direction and it can change in direction, the inertia cannot be expressed in one value. You need to provide a tensor of inertia. Okay? So as a meaning, it's still the same meaning, but now you need to give it several components, not only one component.
هيدا عم نحكي عن البرودكت اوف انيرشيا، ما هيك؟
Yes, يعني أنت هلا we'll see together يعني when we proceed with the slides you will understand why we need to compute all of these inertias.
اوكي ديل. وبعد شغله، نحن
Yeah.
خلصنا الشابتر، ما بتذكر من شي جمعتين نحن كنا بعد في عنا شي
Look,
باراجرافين ثلاثه.
Michelle told me about this. أنا فكرت خلصنا. No problem. In case we still have a section, I will cover it again.
اوكي ميرسي.
Welcome.
اليوم
Okay. So for example, if you look at the following figure, for this cylinder, you have xz and yz, both are planes of symmetry in this case. So you can say that ixy, iyz, and ixz are equal to 0. Okay? Now, we know that in general, for certain geometries, for typical geometries, we'll give you formula sheets where they will mention for you what are the inertias about xx, yy, zz, and also product of inertia. But now if we want to deduce, so if we have all information about this axis passing by G, if we want to deduce inertias and products of inertia about any xyz axis that are parallel to x prime, y prime, z prime, where x prime, y prime, z prime are axes passing by the center of mass, we can do this by applying parallel axis theorem. And you are already familiar with this theorem. So all you have to do, for example, if you want to get ixx, you need ix prime x prime plus m times the distance between x and x prime axis. And you can calculate this distance by, you should do md square. So this distance square will correspond to yg square plus zg square, where yg and zg represent the coordinates of point G in frame x, y, and z. Okay, so because you need the distance between the two x and x prime axis, and this distance can be just obtained by doing yg square plus zg square. The same for if you want to deduce Iyy. So Iyy is Iy prime y prime plus mxg square plus zg square. And for Izz, it's Iz prime z prime about g plus mxg square plus yg square. Now for product of inertia, you can also relate products. So in case you have from the formula sheet Ix prime y prime about g, you can deduce Ixy by doing Ixy is equal to Ix prime y prime plus m times xgyg. Same for Iyz and Ixz. So we can deduce that we can find the tensor of inertia about any three axes parallel to x prime, y prime, and z prime passing by the center of mass. So from here we can define the inertia tensor. The inertia tensor is in the following form. So you have the first row is Ixx minus Ixy minus Ixz. Once you have the first row, you can deduce the first column because as we said by symmetry, Ixy is equal to Iyx and Ixz is equal to Izx. So you just have to evaluate the three products of inertia and Ixx, Iyy, Izz to be able to complete your inertia tensor. Now, how to use this tensor of inertia, we'll see in the coming slides. So an inertia tensor has a unique set of values for a body when it is computed for each location of the origin O and orientation of the coordinates origin. Now, in case we selected a frame in a way to have products of inertia equal to 0, the tensor of inertia will have a much simpler form. So it will be Ix 0, 0, 0 Iy 0, and 0, 0 Iz. So you will only have diagonal elements for the inertia tensor. And we'll see that this will simplify a lot the analysis for us. That's why we try, if we can, okay, to find what we call the principal axis of the body. So these are the axes for which you don't have product of inertia. So we can talk about principal moments of inertia, about the three principal axes, x, y, z. In this case, all products will be 0. So in this case, of these three principal moments of inertia, one will be a maximum and one will be a minimum. Now, what if we need to obtain inertia about any arbitrary axis? So sometimes you are not interested into x, y, z, the familiar x, y, z, for example, that are axes of symmetry. You are not interested in them. You want to find the inertia about an arbitrary axis in your figure. Okay, so you can do this. As we'll see in this section, you can relate the inertia about an arbitrary axis to the inertia about a axis x, y, z passing by O. So if you have x, y, z axis passing by O, And in this frame, you already calculated the inertia tensor. You can deduce what will be the inertia about an arbitrary axis passing by O. All you need to know first, the condition is that this axis should pass by O, and you should find the unit vector UA of this axis. So in case you find what is UA, you can deduce what will be the inertia about this axis. Okay, so the idea is the following. All you have to do is to develop a formula of the inertia about an axis. You know that the inertia about the axis is integral r squared dm. Okay, and you can evaluate this r square as UA vectorial r square, which is equivalent to do UA vectorial r dot UA vectorial r. So if we consider unit vector A as uxi plus uyj plus uzk, and we know that the vector position r is xi plus yz plus zk, if you do the mathematical expansion, of course, you can directly use the final result, okay? So if you do the mathematical expansion of this, you end up with the following formula. And you have the right to directly use this formula, okay? So this formula will state that if I have the inertia tensor about x, y, z, I can deduce the inertia about an arbitrary axis passing by O. The only condition is that I need the unit vector of this axis, and this axis should pass by O. So all you have to do is to use this formula. Ixx ux square plus iyy uy square plus izz uz square minus 2 times ixy ux uy minus 2 iyz uz uy minus 2 ixz ux uz. Now, of course, in case you have if you select the axis passing by O as principal axis, you can consider then the product of inertia will be 0, which will simplify your expression. So in case you have x, y, z are principal axis for the rigid body, the products of inertia will be 0, and this will facilitate the computation of the inertia about any axis passing by O. But you just need to evaluate the unit vector for this axis. Okay? Any question on this? Let us do an example to see how we calculate inertias and how we can use these results after. Okay? So for example, determine the moment of inertia of the bent rod about the AA axis shown. The mass of each of the 3 segments are shown. For example, in which type of problems you might need to calculate the inertia about this axis AA? If I tell you, for example, that this body, okay, this rigid body is rotating about AA axis. So it's the case of rotation, and this axis is fixed. And it's true that you don't have 3D motion here. It's rotation about fixed axis, but you need to evaluate the inertia, and you can say that sum of moments about AA axis, okay, is equal to inertia about this axis times alpha, okay? So you can say this from the analysis in 2D motion, you can say this, but you don't know what is the inertia about this axis, and you want to determine it, you want to calculate it. So to do this, you need to perform this analysis, okay? So to get the inertia about this arbitrary axis, you need to decompose your body into 3 parts. So as you can see in this figure, your body is formed by 3 parts. You have rod AB, you have rod BC, and you have rod CD. And if you want to get the inertia in integration way, it will be complex. So to get the inertia in a simple way, you can say these 3 rods one is parallel to z-axis, one is parallel to x-axis, and one is parallel to y-axis. So it will be easy for me to determine the inertia tensor of this system in plane with respect to the frame x, y, and z. Okay? So all I have to do then is to say, if I want to calculate the inertia about the ixx of this body, about x-axis passing by A, what should I do? I should divide it into 3 parts. I should do ixx of part BA plus ixx of part BC plus ixx of part CD. Okay? For example, let us start with this. If you look at part AB, AB is a rod, okay, and the x-axis is parallel to this rod, okay? Sorry, is perpendicular to this rod. And you know, if you remember, if you have a rod and you have an axis passing by its center of mass and perpendicular to it, okay, you know that the inertia about this axis is ml square over 12. Okay. And you know that if I take an axis parallel to this axis and I apply the parallel axis theorem between the two, I will get that because A is the extremity of the rod. So we know this analysis from 2D. Okay. So if I apply the parallel axis theorem, this distance is L over 2. So I can say that
L squared over 2.
Okay, sorry. So I can say that about A, the inertia is simply Ixx about A is ml square over 3. Okay. Now, if I consider rod BC. Okay. For rod BC, here of course I consider a negligible thickness for the rod. It's not a cylinder. If it has a radius, they should give me the radius. So if for negligible thickness, I can say that if I take an axis parallel to the rod, okay, the inertia about this axis is 0 because of negligible thickness. So if you want for rod BC now, if you take x prime axis passing by the center of mass, BC is along x prime. So x prime for BC is 0. Okay? So x prime is 0. But what I want to evaluate about axis xx. So I use the formula. What is the parallel axis formula? It states that Ixx is equal to x prime plus the mass of my rod BC, so plus MBC, times, as we have seen together, so the distance between the YG plus YG plus ZG square. So YG square plus ZG square. Okay, so here I need to evaluate the coordinates of the center of mass of BC. So this is the center of mass of BC. It's here. Okay. So if I look at my figure, for this point, what are the coordinates? So I need Y and I need Z. Okay. So for Y, it's at the middle here. Okay. So Y of G, sorry, for X of G, this is X of G. This part is X of G. Okay. Y of G, when I do the projection, Y of G is 0 because if you project this point like this, if you do projection for, this is G, okay? If you project it on XY plane, you have that X of G is minus 0.1, but Y of G is 0 because the projection is on X-axis. So we can say that Y of G is 0. So we only have to consider Z of G. And Z of G is equal to 0.2. Okay, so I replace Z of G by 0.2, and I can deduce the value of Ixx for BC. Okay, now I still have Ixx for CD. So if I take now CD, I should say do the same for CD. If I take an axis x prime parallel to x, the inertia about this axis, since this axis is perpendicular to CD, the inertia is ml squared over 12. And now I need to apply the parallel axis theorem. So I should do Ixx plus Ix prime x prime plus mass of CD. Okay, now I have the same formula, but now I need to compute it for G of CD. Okay, so I need to evaluate the coordinate YG of CD and ZG of CD. This is the center of CD, it's here. So to evaluate the coordinates of this point, first, X of this point, according to the figure, is minus 0.2. So for coordinates of this point, I have first minus 0.2 in X. Now, if I do my projection here, I have that the Y component of this point is 0.4 over 2. So this distance is 0.4. Half of it is 0.2. So the second coordinate is 0.2 for Y. And for Z, I have an elevation also of 0.2 meters. So I have Z of G is of CD is plus 0.2. So now all I have to do is to replace in the formula to get Ixx of CD. Okay, and once I have the three inertias, I will sum the three of them to get Ixx, total Ixx for this body. Okay, so I should do the same to evaluate all my terms. Okay, so I should evaluate Ixx, Iyy, Izz, Ixy, Iyz, and Ixz. All I have to do is to plug in the formulas of product of inertia and of inertia. I should replace in parallel axis theorem. You can please try to practice on this. So it's very simple. All you have to do is to get coordinates of the center of mass for each of your part, AB, BC, and CD. And once you do it, you just have to go to these formulas here for products of inertia that we have developed together here. Okay, so Ixx is Ix prime x prime plus myg squared plus zg squared. Same for Iyy, Izz. And for products of inertia, you just have to do Ixy, which is Ix prime y prime plus mxg yg. But here, if you want, since all of your geometries are rods, okay, for rods, you have two planes of symmetry. So all products of inertia will be 0. Because if you take x, y, z in this way, these are principal axes passing by the center of mass. xy is an axis of symmetry and is a plane of symmetry. And xz also is a plane of symmetry. So you can deduce that all products of inertia for a rod will be equal to 0 when you consider x prime, y prime, z prime passing by the center of mass. Therefore, to compute the product of inertia for each rod, you just have to do the mass of this rod times, for Ixy, you do times xg of rod times yg of rod. Okay, so in this way, you can evaluate your products of inertia and your moments of inertia, and you will be able to calculate about x, y, z, what are the tensor of inertia. And once you get all of these by replacing in the formulas, you need to evaluate now the unit vector. So your unit vector is AA, okay? This axis AA. So you need to evaluate the coordinates of point D. So A is the origin, so 0, 0, 0. For point D, all you have to do is to project first D on X and Y. So X component of D is minus 0.2. Y component of D, if you do projection on XY plane, you have this distance is for Y of D, it's 0.4. And finally, you have Z of D, since this point also is at an elevation, so C and D are at the same level of elevation. Same for B, so the elevation is 0.2. So now, you know, to get the unit vector, all you have to do is to say unit vector of AD is AD vector over AD magnitude. And since A is the origin, so coordinates of AD vector will be minus 0.2i plus 0.4j plus 0.2k, okay? And for the magnitude AD, it's radical of 0.2 square plus 0.4 square plus 0.2 square. So you can evaluate the components of your unit vector. So as you can see here, it's just AD vector over AD magnitude. And then the components, this component is ux, this is uy, and this is uz. So now if you replace in your formula, you can deduce the inertia about AA axis. So now if I tell you you have rotation about this axis, pure rotation, 2D motion, then you can use this inertia and say that sum of moment about this axis is I times alpha vector. Okay. Any question on this? Okay. Now, what about the angular momentum? So we know from previous analysis that the angular momentum
دكتور
is, yes?
سوري انت هلا بتكون لقيت الاي اي اي بتكون لقيت المومنت اوف انرشيا اباوت هذا الاكسس يعني قديش
Yes.
في عنده capacity انه to oppose rotation about هذا
About this
الاكسس.
axis, exactly. Yes.
اوكي مش يعني مش هيك كنت عم تقولي لي هلا لما نوصل برودكت اوف
Exactly.
انرشيا.
Yes.
لا انا اوكي بس انه هو هيك وحده برودكت اوف انرشيا ما له مينينج بس انه هو بيساعدنا
ما له meaning
بالمومنت
بس
اوف انرشيا.
بتعوزه يعني
اوكي
حتى هلا بنشوف حتشوفوا بعدين كمان بتعوز التنسر in other applications. هلا we'll see how.
اوكي ميرسي كثير.
Welcome. Okay, so XYZ coordinate system represent an inertial frame of reference, and its axes are fixed or translating with a constant velocity. The angular momentum is measured from this reference will be computed relative to the arbitrary point A. So let us consider, as we said before, we have a rigid body and we have rotation about an arbitrary axis. So we can do the general analysis by considering at A translating frame, okay? And then you know that we can decompose and we can get the velocity of any point in this body relative to point A using the formula that V of any point is V of A plus, which take into consideration translation of A, plus total omega vectorial AG, okay? So now, in this type of frames, if you want to evaluate the angular momentum, we know that the angular momentum of a particle is defined as RA vectorial MIVI, okay? So whenever you have a rigid body and you want to compute the total angular momentum of this body about a certain axis, all you have to do is to integrate over the body. And you can replace velocity of each particle by VA plus omega total of your body vectorial RA, where rho represents the distance between A and the particle I. So if you perform the integral procedure, and as you know, it's always the same method. I need to integrate over the whole body, and I can get a general expression for my angular momentum about a certain point. Okay. Now we start to take some particular cases. Okay. So for example, if I have rotation about fixed point, I can put my point A on point O. So if you put point A on O, what will happen? Velocity of A will be 0. So if you go back to this equation, since if A is fixed, VA will be 0, and just you will have to integrate omega vectorial distance of each vector position from for any particle from point O. Okay, so if we take this particular case and we perform the integral procedure, we'll get a certain expression that we'll see together now. Another important application is to take point A at the center of mass. Okay, so if I take A at the center of mass, we know that by definition, what is the property of center of mass? When I perform integration integral m rho A dm, so if I take A at center of mass, integral rho dm will be equal to 0, because this will be equal to rho of g times total mass. And since you have g is the origin, so if we take A at g, we can simplify the expression. So that's why it's of interest to take particular points, because particular points will allow you to simplify your